I hope everyone got it that we're starting at 2. Okay, so like as I said, those are the two passive devices you'll be dealing with in IC design most of the time, the resistance and capacitance, because everything is a resistor and a capacitor. The next thing we are going to look at is diodes. So diodes is also another thing which you have to be familiar with, but mostly you're worried about the reverse bias diode than anything else, because all your source, drain junctions, wells, everything is basically a reverse bias diode. So what we'll do is we'll look at the reverse bias diode and derive some expressions for it, which will be actually useful for our MOS derivation as well. So some of the diode stuff will just kind of browse through it, like the forward bias junction current. I'll just give the expression and go through it because we'll really never use it, at least in this course. But for the depletion charges and all that, we'll go deep into that, because a lot of that calculation and derivation will be needed for doing MOS calculations as well. Okay. So, but before I introduce diode, and I mean, almost all of you are familiar with semiconductors, but we'll do a quick review of semiconductor. Um, from a material band gap perspective, we'll do a quick review. Okay. So in a semiconductor, I'll show a graph, just showing you different materials, mostly 3 types of materials we deal with. You've probably seen band diagrams for materials. Essentially, what the band diagrams is, band diagram is a very it's a concise and a very classical way to capture some materials conduction property, basically. Okay, so if you want to know how this material is going to conduct, if I do so and so, if I want to apply voltage so and so, I mean electrical properties, not just conduction, but electrical properties. So instead of because most of the properties, electrical properties of semiconductors, they're quantum mechanics related, right? Or statistical mechanics related. So you don't want to dive deep into those details for finding out what forward bias current is, right? So the band gaps are actually derived from a momentum plot from quantum mechanics. But so you basically, what you do is you kind of capture a subset of that to what you need. And what we need is, we basically want to know mostly the conduction property of a material, and the band gaps kind of capture it very well. And the beauty of the band gap is, using that, you can start playing around with materials and engineer materials. There are a lot of devices which have been created, just people playing around with band gaps, like a lot of your power amplifiers actually have a device what's called HEMT, and those devices were actually purely fabricated out of people playing around with band gaps. I mean band diagrams. So that's why I think band diagrams are, at least for just knowing the overview of it is a good idea. And essentially what the band diagrams are, it's like, for example, if you look at this band diagram here, the x-axis is actually the length of the device, or whatever you want to call it. Let me just quickly draw it. It's like I dropped my pen somewhere. So you basically, if you have a slab of material here, so it's assuming that it's homogeneous, and this band diagram applies to this whole length here, right? So, and typically if it is in steady state, this whole band diagram in x-axis is basically the same. Um, and what it basically tells you is the allowable energy states for electrons, in the sense that if you've read the classical atomic structures, what are the allowable states in an atom, right? So it basically captures that in a more um, kind of a, with all the lattice and everything else, right? So what you have read in your physics is, in isolation, if I have a silicon atom, then there are electrons moving around it, and what are the allowable energies in that, right? And then once you start putting the devices in, those allowable energies start splitting, and they start becoming these bands. And then because of this lattice, now this, you have an entire band instead of having one state. And that's what the energy band diagrams capture. Basically, they're telling you what is the average, this is the electron energy, and for this particular material, what are the available states within these energy levels, and that tells you if something is going to conduct or not conduct. And one of the most important um, parameters in a band diagram is what's called a Fermi level. And what that tells you is that uh, and it is, most of the time, it's a fictitious level in semiconductors, in the sense that it tells you what level of energy uh, your the probability of electron occupying that state is half, right? And that could be actually a forbidden gap, like this. This is a forbidden gap. No allowable energy is allowed in this for a semiconductor, for example. But your Fermi level is usually in between it for intrinsic conductors. Fermi level is in it, basically telling you, on average, what is the probability of half the electrons in this state, which means that half of it is here and half of it is here. That's why the half lies in the middle. So it is a probabilistic, it's a statistical thing to measure. So that's the Fermi level. Okay, so this is a band diagram shown for what's called an intrinsic semiconductor, right? So you have a valence band which tells you if you have holes below this energy level, then your material is going to conduct. If I apply electric field, then you'll have motion in your charges. If you have electrons, then they need to be above the conduction band. If there are certain energy states occupied, these are the available states. If they are occupied, then you can apply a voltage which will create electric field, and you'll have motion of charges, and you'll get current and so on, right? So that's the whole idea. Now, if you I haven't drawn the Fermi level here. So in an intrinsic semiconductor, the Fermi level is, I think I have another slide which I'll show it, but I'll just quickly show it here. So the Fermi level is halfway through, because in an intrinsic semiconductor, what happens is at room temperature, some electrons will get enough energy to move to the conduction band, and every time an electron moves in, it leaves a hole behind. So I'll just draw it on the surface. Every time electron moves here, it leaves it. So essentially, as many of electrons you have, you'll have that many holes here. That's why the Fermi level. So the probability of a electron state occupying is right in the middle because of that. So this is what's called an intrinsic semiconductor, which is pure crystal, no impurities added. Now, if you take a 5 element, which has one extra, which has 5 electrons on the outer shell, if you take any of these elements, and typically you can't use all of these, some of these just won't work with silicon. Like antimony is probably the one which is used most, the SB, or phosphorus. Actually, phosphorus is another one which is used quite a bit to dope it. This is what's called doping. So you're doping with the impurity such that one of the atoms sits in between, let's say, silicon atoms, and because it has an extra electron, mobile electron, it's kind of free to move, and that immediately jumps into the conduction band. And once it does that, it leaves a positive charge behind it. It's not a hole, by the way. It's just a positive immobile charge, basically. The hole is, it's a different one. Here, it's just immobile charge. And So you can do conduction in electron using this 5 compound. So this is adding impurity to increase your conduction in a semiconductor. You can do the opposite where you take a 3-type element, for example, boron, and you add it. And here you actually have one less electron. So you have like basically a bond hanging, and that kind of sort of signifies hole, which is sort of a positive charge. So your Fermi level is closer to the valence band, which means that there are a lot of holes already in the valence band, very close, already in the valence band. So you apply electric field and it'll start flowing. Um, and based on this, you can actually um, partition or what's the right word for it? Classify materials according to it. Like for example, you can see here insulators. So insulators have their valence band and conduction band separated by a huge band gap. This is the forbidden band, and it takes a lot of energy for you to take any electron and put it. Usually that energy just breaks the insulator, whatever. Oh, I should have mentioned it. I'll just mention it now. When I was introducing the dielectric in the capacitor, one thing I forgot to mention is that those dielectrics or any even air, they have what's called a breakdown voltage, right? So as you are applying voltage, higher and higher voltage, higher electricity field is created because more number of charges are on the plate. But at certain point, what will happen is I was showing you that the dipoles are stretched, right? And it kind of looks like a little tadpole with positive and negative end at the both ends. But there is a certain electric field for every material where that thing will rupture and it'll break down. Okay, so that's what's called dielectric breakdown, or in case of semiconductor, CMOS especially, it's all oxide, so you call it oxide breakdown. So for example, in 0.18 micron technology, the thin oxide, which is the gate oxide, it's about, I think it's about 27 nanometer or 27 angstrom, I forget. Uh, yeah, 27 nanometer. And because it's so thin, if you and the dielectric, so the electric field is voltage divided by distance, right? So as if you have given voltage and you keep reducing the distance, then the electric field is just becoming bigger and bigger. So that's why the breakdown voltage for those transistors as the oxide is getting thinner is also lower and lower. For example, in 0.18, let's say 1 micron technology, the voltages were 5 volt. So you could almost apply 6 volts to the gate and the oxide will be fine. You come to 0.18, it's scaled almost like 5 times. Not 5 times, maybe less than that, because they do a lot of engineering in that, process engineering. So in 0.18, for example, you apply the usual voltage is 1.8 volt. The breakdown voltage is around 2 to 2.2 volts. So you apply 2.2 volts, then the oxide will break down and your chip is no good anymore. So just remember that. So usually there is no conduction. So like in this band gap, you might think, um, if I apply high enough voltage or if I heat it, then some of these electrons will go into conduction band and start conducting. Actually, it just breaks down and becomes what's called a degenerate material. Okay. Okay, so that's the insulator. Before I get to the semiconductor, let me get to the conductor. So in conductor, the conduction and the valence band are actually just squished together. In other words, there is always a lot of electrons available in the conduction band, or if it was a conductor with valence, holes, then it will be all holes there. Okay. So you always have, even at room temperature, you have plenty electrons to conduct. So which is basically aluminum, copper, and tungsten. These are all your conductors, obviously. So now in between is the semiconductor, where you have a forbidden energy states, a gap, which is called the band gap. But it is much lower than, for example, the insulators. And obviously it's not butting each other, because then, it'll be conducting all the time. And then what this allows you to do is um, now allows you to engineer it electrically, right? So basically you have a band gap. So for example, in silicon, this is about 1.1 electron volt. Now, at room temperature itself, some of them break the bonds and switch to conduction band. And like as I showed in the impurities, you can add some impurities and make some of these electrons available in the conduction band even at room temperature. Uh, but the whole idea about the semiconductor material is you want a controllable monitor, right? Because what we are getting to now is like what we're trying to do is active devices, right? And just to give you a quick kind of motivation on why we are trying to do active devices is because so this is obviously a digital design course, so we'll stick to digital. So in digital, you did all your logics, right? With week one, Puneet's class, you did the logic, which were all 0 to 1, right? Everything was expressed in 0 to 1 and some high Z's and all that. But this is just an abstraction, right? There is no reality in this. There is no circuit which says, okay, this is 0, this is 1. Like, for example, your computer programs can do it. But in reality, circuits have physical parameters. Either it's current, charge, voltage, electric field, magnetic field, or whatever it is. You have to represent them in these physical parameters before you can start doing computation or any sorts of manipulation in these digital worlds, right? So, one of the most popular ways, which is, like I said, there are many ways to do it, but one of the popular ways which is done is basically you have a supply voltage, which is essentially your battery, right? So you have a battery in your circuit, and what you want is you want a switch which connects to the output if you want to represent a 1, or you want a switch connected to ground at the output if you want to represent a 0. Or more realistically, you want a resistor with a switch to the output. So this is VDD, and you want to switch with a resistor to ground at the output. So if I want to represent a 1, I switch on the switch. Uh, if I want to represent a 0, then I do that. Obviously, you can swap them. And if you say, no, I want to do 0 when it is VDD. But obviously, uh, it's a, it's a headache for other people to understand your stuff because convention is this. So that's the idea. Now, obviously, this you cannot do with a passive device, right? Passive device is just a resistor or a cap. What you want is you want a 3-terminal device, basically, which controls the resistor like a controllable resistor. So you want somewhere where you can control with a voltage, and that switches this resistor between VDD or ground to this node. That's what you're looking for, right? And that's what we're trying to create with this semiconductor material, because we can't create only with the insulator or with the conductor, because we want this control element. And that's where semiconductor comes into it, because you're taking this material which can behave differently either with applied electric field or magnetic field and so on. Okay. So I'll just quickly show some of the band diagram stuff, but I'll show you more, give you some more numbers now. So if you take just a pure crystalline intrinsic semiconductor. So intrinsic means it's not been doped, so pure crystalline structure. And I just explained that the band diagram will have the valence band, conduction band. And like as I said, you at room temperature, there will be enough energy for some of the electrons to break their bonds and move to the conduction band. And so, but it'll leave a hole behind or a positive charge behind. So Fermi potential, which tells you the probability of electron, the energy at which the probability of electron is half, is almost midway between EC and EV, because every time an electron goes, it leaves a positive behind. So um, that's why. Okay. And typically the intrinsic carrier concentration at room temperature is about 1.45 10 to the power 10 electrons per centimeter cube. So these jumps which I showed you, if you take a volume of 1 centimeter cube, it's about 10 to the power 10. Or if you take 1 micrometer cube, I think is too little. Like 1 micrometer cube is 18 10 to the power minus 8. So you obviously don't have electron in 1 micro. But if it is looking large for you, to just give you an idea, the density of atoms in silicon is about 5 into 10 to the power 22 per centimeter cube. So you're talking about one carrier in 10 to the power 12 atoms. So a intrinsic or a crystalline semiconductor is very resistive. Basically, it's hardly conductive at room temperature. Although number of carriers looks huge per centimeter cube, but if you look at it in a relative sense, it's pretty small. Um, so the electron concentration, the N type is what's called the intrinsic concentration, which I just showed you on top is 1.45 to the 10 to the power 10. The whole concentration is also the same because every time electron goes into the conduction band, leaves one behind. And there is a law called mass action law, which if the semiconductor is not degenerate, I'll explain what degeneration means, is always valid. And that is basically saying that the product of the electron concentration times the whole concentration is equal to Ni square, which is the intrinsic semiconductor times the square of that. Okay, so that's just a law which is applicable to semiconductor as long as it's not degenerate. Okay, now let's look at a doped or what's called extrinsic one, and we'll look at the N type, which I just showed you. So now what we do is we take the same block of material, but we dope it with a dopant, which has extra electron. And then, like I showed last time, the Fermi potential gets closer to valence band because now the probability of finding electrons in the conduction bands is much higher. So the half point also moves along with it. So phosphorus is obviously one which people do. So phosphorus gas is passed for diffusion to create an N-type material. For example, if you want to make an N-well, like yesterday I was showing you, you take the mask, you do a cut on the mask, you raise it to a really high temperature, pass phosphorus gas, and it will diffuse in that mask area and create an N-well. Okay, and this potential difference is actually a very important quantity which use a lot in deriving a lot of the device parameters, and that's called the Fermi potential. So Fermi potential is basically the difference in potential between the intrinsic and the extrinsic Fermi levels. Okay, and that is given by this expression, which is the thermal voltage, which is about 26 millivolts times the natural log of the ratio of donor atoms versus the intrinsic atoms. So you can see as you keep increasing the donor atoms, then this separation keeps increasing, and it's a logarithm. So what happens is it just doesn't, it kind of flattens out, right? Obviously, it can't keep going above EC. Then it becomes degenerate, basically, if it does. And these are some of important numbers because if you dope it higher, if your doping concentrations are higher than these, then they become degenerate. So for example, the number of atoms, as I showed, is 10 to the power 22. So if you take a lot of phosphorus irons and get it close to this, then it's no more a semiconductor. In order to become a semiconductor, so people, these are kind of limits people stick to. This is obviously through both from physics as well as experiment and empirical data. If you want to heavily dope something, you want to remain in this 10 to the power 18 range. If you want to lightly dope it, then you remain in the 10 to the power 15 per centimeter cube range. And the Fermi potentials for these dopings I kind of show you, so just to give a feel on the numbers. So for this is about 0.45. So if you've heavily doped it, since this is close to, so this is about 1.1, right? The entire band gap here is about 1.1. So which means this is about 0.5 difference. So as you keep doping it, this difference keeps increasing. So you can see as you go from doping from 10 to the power 15, which is 0.25, means the Fermi level is somewhere here. And then when you start doping it higher and higher, it gets closer to the conduction band, and the separation obviously increases. And you can calculate the electron concentration and whole concentration at room temperature using the expression I showed before. So the electron is pretty much the same as the doping concentration. So let's say you've done 10 to the power 18 per centimeter cube of doping of phosphorus, then your electron concentration at room temperature is pretty much equal to that, right? Then the whole concentration, you use the mass action law. So you know the doping concentration at room temperature for intrinsic one, you take the square of that divided by 10 to the power 18. You can see it's 200. So you can see that's why, in semiconductor, this is called the majority carrier and this is called the minority because, essentially there's just no holes in this if you're heavily doped. Same thing with the p-type. So p-type, you take something like boron and the Fermi level actually drops now closer to the valence band. And then the Fermi potential is given by the same number, but it's a positive number now because it's the Fermi level minus this. In the N case, it was Fermi level minus this, so it was a negative number. And so that's why it's Na, the acceptor concentration divided by Ni log of that and thermal voltage. So you get this. And the voltages are, because the ratios are the same. So same thing, about 0.45 volts for 10 to the power 18, about 0.25 volts for 10 to the power 15 here as well. And similar calculation, because for holes, it's pretty much equal to the concentration of the acceptor ions. Okay, so PN junction, I'm going to go a little deep into the calculation of calculating, especially the charge in the depletion area. And the reason I do this is because we use this expression a lot in, a lot of the derivations in VT calculations or body effect and all that um, in our MOS. So I thought it'll be good to sort of, show you. Now, you can just follow it in a very, just follow the logic behind it, even if you're, the expressions are clumsy and you feel like it's going out of hand. Just follow the logic of it. What are we trying to do? Because that's very key when you're trying to understand some of the physical effects of the MOS as well, because essentially MOS has a lot of the parasitic diodes as well, the source bulk, source to drain to bulk, and so on. Okay, so let's take a P plus type material, and so in IC design, every time we put a plus or a minus, it means how heavily or lightly it's doped. So when it is P plus, you can see I've taken a heavy concentration of acceptor ions. So this is heavily doped. And then I take an N type of material and I dope it with N type material, and it's just a little bit lightly doped. So N type material, and then I join them. Okay. So when you join them, the electron energy on this side is higher than this side. And thermodynamics basically says that at equilibrium, they have to be same. So what will happen is these electrons will start moving into the P side. So, and as they're moving to the P side, they obviously leave a positive charge behind. And every time they leave, they're leaving a positive charge behind. Each positive charge creates electric field between this positive charge and this negative charge, which means that then for the negative electron, these are a force against it, right? Because the force is, the field is in this direction. For negative charge, the force is in this direction on the from P to N side. So as the number of this is what's called depletion charge. It's called depletion because the atoms are depleted of their carrier, which is electron in this. So majority carrier is electron. So that's why it's called depletion. Okay, and these are immobile. You can't conduct current through this. It's just basically the overall charge in this unit volume is positive. So as they're moving, they're building up this electric field. The forces against the electron is increasing. At one point, the force in this direction and the potential difference which is existing between the electron and this actually equate, and then it stops, right? And that's what's called the built-in potential. So if I draw the band diagram, again, what thermodynamics tells me is that if I take any material, if it is joined together or amalgamation of or anything, at steady state, the Fermi level should be constant. It should remain steady state. You cannot have a Fermi level which is going kind of like that in a steady state one. If you and when I not only steady state, no fields applied either. If I apply some electric fields on this side, then the Fermi level obviously will change. But without any fields applied, then it's just constant. Now on the semiconductor on the left of this charge, I know it is still a P plus type, and I know the band diagram should look like a P type. The semiconductor on the right-hand side of the space charge is an N-type, and I know the N-type should look like this because this is the Fermi level close to the conduction band. So, which means that the band is kind of bending sort of from the P-type to N-type. And this potential difference is essentially the Fermi potential difference between the P-type and the N-type. All right. Okay. So, and depending on the doping concentrations, you get a length of this charge which exists. So obviously I've shown it equal on both directions, but you can see because this is heavily doped, this side is going to be thinner and this side is going to be larger because for the same electric field or because the charges have to be equal. The charges have to be equal and this doping concentration is small, you need a larger volume. If you need a larger volume, you need a larger length here, right? So just want to make sure I haven't drawn it to scale here. So it's just showing you that charge basically. It's just showing you that the charge on and this is charge per unit volume. So the charge per unit volume is basically the same as your doping concentrate. So you have a positive charge on this side and then you have a negative charge on this side as you are sort of traveling through the semiconductor, right? And the value of that is Q times ND, which is the doping concentration times the electron or the whole charge. Now, if you plot the electric field across it, and just bear with me. I mean, I'm just taking you step by step and I'll sort of give you an idea why we are going through all this. So what type of calculations we are trying to do. So now if I plot the electric field across it, it is essentially the derivative of this potential. Or in other words, you can see that because the charges start here, so obviously the electric field is 0 here, and the charges are there increasing, then obviously the electric field starts increasing. It's the peak at the very junction. Then the electric field starts terminating on the negative charge, which means that it slowly start decreasing, and it is um, 0 after the depletion area, right? And I haven't drawn to scale here. Again, this is not exactly linear. So what we're interested in is in calculating this depletion charge, right? And this depletion charge calculation is a key, calculation we use a lot during our MOS calculation also. So that's why while introducing it to PN junction, I, sort of decided to introduce this, how to calculate how much charge is inside it. So if you know the doping concentration of a silicon material and they're joined together, what kind of charge is accumulated in this depletion area and what's the length of this charge. Actually, once you know the total charge, you actually know the length because you divide it by the volume concentration for it. Okay, so I'm just, kind of splitting so I'm just kind of taking the slice of just the immobile charge area. So we have a depletion charge of all the positive charges, which is all the electrons are gone to this side, and this is the negative charges, right? So as I showed here, the peak electric field is right in the middle here. And this distance is xn, which is basically telling you depletion length of the n region, xp, which is the depletion range in the p region. And obviously the charges are equal. So the charge on the QP side is negative charge because it's all electron. On the N side is positive because of the electrons which are missing here. And this total QP is charge of electron times the acceptor density, whatever you have doped it with, the concentration of the doping concentration times this length, right? This length if you take it. So essentially what it is charge per unit volume times the volume is what you're trying to do. So this charge per unit volume times the volume. If you do that, you'll get this. And obviously, this you can see that um, the length, the ratio of the lengths of the N side to P side is the inverse of the doping concentration, which I just explained why that's the case, which is kind of intuitive. Now, if you use Gauss's law, so again, as I had explained in the morning, if you take this volume and enclose it, right, to the surface, and basically the Gauss's law tells, and here all the electric fields are coming out obviously on one side. So if I take a unit area and you take the P, then it is basically QP, the charge, total charge or unit charge, depending on what electric field they are computing, divided by the uh, permittivity of that material. In this case, it's a silicon, so it's a permittivity of the material, which is about 12 times that of free space, right? So then obviously you substitute this equation here. So it's Q times donor concentration times the length of the depletion region divided by epsilon S is equal to this, and so on. So that's the expression, and I'll show you why we're using that expression. Now, if you look at this, if you just look at the potential, the band bending on just one side, that you can show it to be the peak of the electric field times the XP divided by 2. That you just, if you assume this is linear, I mean, that's an approximation, but it's a pretty good assumption. If this is your assumption, then you can say this peak divided by 2, because what you're doing is you're taking this triangle, dividing this, you're taking the average of it. Basically, you're just saying the field is average of this times XP is the voltage across it. So it's V over D, but here E is not constant. So you're taking the average of it, and that's E peak over 2 is what you're doing. So that's an approximation you do to calculate the potential difference on one side. Same thing, the potential difference on the N side is the peak, but times the length of this region divided by 2. And if you substitute the expressions from these equation into XP and XN and E peak and E peaks, the peak value of the electric field, and you add those two together, the two potentials together, then it expands to this expression here, which is essentially tells you the function of Xn and Xp as the doping concentration and your Fermi potential difference. Okay, and then if you using this expression Na equal to Xp, substituting here either Xp or Xn, then you get what is the length on one side as a function of doping concentration of Na and Nd, right? So if you know the acceptor concentration, if you know the doping concentration, then you know what's the length of this depletion region. Okay, or if you want to see the N side, you can do the same thing and see the N side as well. And this is usually assuming that the other side is very, very heavily doped. If it is not, then this is not an accurate expression, but it is still pretty close. This is what I call it, the one-sided expression. I'm sorry, this is the accurate expression. This is the one-sided expression. So the one-sided expression is if the Na or Nd is heavily doped compared to the other one, then you basically take one of these expressions and make it 0, and then you just know uh, the length of the depletion on one side. Again, this expression is again very useful on in MOS devices. Because in MOS devices, usually what you have is you have very heavily doped on one side, and then there's a depletion on the bulk or the N well, and that's really what we're interested in calculating. So that's where we actually use this expression. Okay. And then if you want to find out the total charge, obviously the total charge is the volume, unit volume times the Xn. And the charge per unit length times Xn, and that gives you the total charge of that QBN. Okay. All right. So just recap quickly. What we are interested is, mostly trying to find out if we take a semiconductor and attach it to another one, uh, what is the depletion area and how much charge is it capturing? Okay, that's essentially what we are trying to capture. So what we did was you first use the band diagram to show that there's a potential difference that gives you the difference in the electric field, and using that electric field and potential difference using Gauss's law and Poisson equation, which is a corollary of the Gauss's law. Using that, we got the expression for XP and XN. Okay. So again, so if you find this thing is very clumsy, just understand the overall process. Like as I said, our goal is to find out if there is a contact between two types of semiconductor. We know there is a depletion region which is going to get formed. I want to know how long is that depletion area, or how big is that depletion area, and how much charge is in that depletion area, which is 1 to n. Okay, so any questions? Okay, all clear? All right, so all we did, like as I said, we got expression for the length of the depletion and the charge enclosed in that depletion, which is once you find the length, then you know that once you know the concentration. Okay, so we're going to quickly look at the forward bias junction and the reverse bias. Forward bias, like as I said, I'm not going to derive the equation, just give you the expression so that you know. But if you take a P plus junction, you saw that you know the potential. So you'll get a built-in potential where the plus side is on the N side and negative side is this. And given by this expression, thermal voltage times the log of a product of the concentration divided by the intrinsic concentration square. So that's your built-in voltage, which is depending on how you fabricated it, anywhere between 0.45, 5.5 volts to almost close to 0.7 volts. Okay, in the forward bias, what we do is we apply a potential difference across it, but we put the positive potential on the B. So we are trying to now negate the barrier, right? So the barrier is tending to be the positive side here. So if we put a positive voltage here, this barrier will keep increasing, but we're trying to break the barrier right now. So we put a voltage across it. And so first we have to overcome this barrier. So you'll see that, whatever this 0.45, 0.7 volts, most of it, but there is, while we are breaking the barrier, there is a current, right? You have diffusion current, mostly diffusion current flowing during that time. And so we apply, and as we keep increasing the voltage, and as you can see, after you break the barrier, it just exponentially increases with reference to the voltage applied across it. So the typical expression is actually one minus this, but approximately it's the saturation current times the exponential of this voltage across it, across the P type. And the saturation voltage is directly proportional to obviously the doping concentration and the area. If the area is big, obviously the current is going to be big. And obviously just like with the capacitors, if you put a reverse bias voltage, if you do the opposite and you keep applying it, there's always a certain breakdown voltage which it will break down after some time. Okay, the reverse bias, actually, from a IC design perspective, the reverse bias is more interesting. I shouldn't say more interesting, I should say everything is interesting, but more useful maybe, because pretty much like I said, if you have 1 million inverters in your thing, then for each inverters you have 4 forward bias diodes, then you have diodes for your bulk and all that. So you're talking about at least 4 to 5 million diodes, which are all reverse biased. You're not forward biasing them, you're just reverse bias. And they're obviously parasitic in nature because that is what you get from those active devices. And now what we do is we apply the voltage in favor of this barrier. So we apply a positive with respect to this, negative with respect to this. And when we do that, we increase this barrier because now we have given the electrons that extra potential to overcome that electric field which stopped the electrons from flowing before. Then obviously after some time they'll again reach a barrier for a given voltage, right? Um, the the interesting thing is that if you look at it from a two-terminal perspective, right? So let's say somebody gave me this box. Somebody gave me a box with this two-terminal. I applied a voltage and I saw some charge build up. Okay. What are you going to assume inside this box? What kind of device is inside this box? So for example, I give you, yeah. So I give you this box with two terminals in it. And what you did is you apply a voltage first and you see there is no current flowing through it. Okay. Then you apply a little delta V on it. Then you see initially there is a little current flowing, so some charge going in and then it stops again, right? So what do you think is inside this box? What kind of element can be this inside this box? So I want some answers. Everybody got the question? Some positive element. What do you mean by some positive element? What I'm asking is what circuit element? Okay. What kind of circuit element can be inside it? Could it be a resistor? Could it be a capacitor? Could it be an inductor? Could it be, some other device like a diode? Well, what would you first assume? Okay. So some people are saying diode, some people are saying resistor, some people. Just with the experiment I performed, by the way, I didn't do any IV characteristics. I just had a voltage. I applied a small delta V and I saw some charge go in and then stop. What kind of resistor it is? I mean, what kind of device it is? Okay, so a lot of people are saying resistor. Some people are saying capacitor. Okay, so people who are saying resistor, I have a resistor. So somebody gave me this inside a box, right? So by the way, maybe I didn't make it clear. IDC is equal to 0. So there's no current flowing through it, right? So, but if I apply a voltage, then there will be a current flowing through this, right? There'll be some I which is equal to V by R. There'll be a current always flowing through this. So yeah, the answer is, if I didn't know anything about it, I would say it's a capacitor, right? So because there is no DC current flowing through it, it's just that when I give a delta step, I see some charge flow through it and then it stops, right? Which means that my best guess is actually that there is a capacitor inside it. Okay, now my next question is this. So I tell you that there is a capacitor. So I think a lot of you, uh, got it as a capacitor. So now I want to find out what capacitance value it is. So you gave me this box and you said, oh, you have these two elements. I don't know what it is. I said, okay, let me apply a little delta V and see what happens. And say, oh, some charge got carried away. And then you'll ask me like, okay, if you say it's a capacitor, what is the value of this capacitor? How would I find that out? Del Q by del V. Exact. Very good. So here, because I don't know what the absolute value is, I'm going to do differential and find out, right? So by the way, when I explained capacitor, I mean, this was taken for granted. I didn't say it, but obviously, everyone, um, you know that Q equals to CV. So if I want to find out the change of current flowing through a capacitor for a change of voltage, then you basically differentiate both the side. If the capacitor is a linear element, then it is C times dV over dt, right? So this, I think, okay. So exactly. So Abhinav, I think you got it right. So this is dq by dv, or in other words, in my kind of explanation, I want to find out how much charge got sucked in when I change this voltage by delta V. Okay. So that's exactly the principle we are going to use to basically calculate this uh, reverse bias capacitance. Because what happens in reverse bias is it actually looks like a capacitance. Because like as I said, I apply a delta V and I see some delta Q charge build up. So basically when I applied the delta V, I saw some charge flow through this, which is delta Q flowing out of this. So how do I find out what the value of this capacitor is? I find out what this delta Q is, and I obviously know what delta V is because that's the voltage I have applied. So I apply a voltage delta V, I find out what delta Q is, and that gives me the expression for the capacitance of this reverse bias diode. And this is where we are going to use the expression what we described last time. Okay. And clean this up a little bit. So I call this quantity CJ because that's the, every literature you'll find it called CJ. It's basically capacitive junction capacitance. That's why it's called CJ. So what I'm interested in finding out is what's the delta Q for delta V. So I'll break this into two separate sort of differentials. One, I'll first find out what's the delta Q for a delta change in the length, right, in um, this thing. And then I find out what is the delta xn for a delta V, or in differential form, I find out what is the change in Q for, what is the derivative of Q with respect to xn, what is the derivative of xn with respect to dV. If I multiply that, I'll get my quantity I'm explaining. And dq is nothing but the volume density times or the charge density per unit length times the length, right, which we used last time. So you can get dq over dxn. So this quantity now you can get from here. That's easy. So now I want this. So basically what I want is I want to take the expression of xn, which I derived last one. So if now I want to find out this. So this expression is here. Now I want to find out this derivative here. So basically what I do is I know the expression for xn from my previous equation. I differentiate it with respect to VR, which is the reverse bias voltage, which is nothing but the voltage across the barrier, which is the built-in voltage plus the applied voltage from this battery. In other words, if um, I just take the junction, right? This built-in voltage was phi naught, right? That's your built-in voltage by definition. Then I apply a reverse bias voltage, right? So that's where in my previous equation, that's what I substituted. And then I differentiated with respect to VR, and that's what I get for here. Because I'm interested in the delta L. So if I go back to the previous one here. So here, if you remember, I had expression for Xn as a function of this built-in potential here, right here. And what I'm going to do is I'm going to add this built-in potential plus the reverse bias voltage because it is in favor of that built-in potential. Right. So, and then I differentiate with respect to VR. And once I do that, then I get the expression for the entire capacitance, which is this term over here, which we call it CJ naught, or in other words, the unit area diffusion capacitance for 0 reverse bias voltage. And then it is dependent square root of phi naught plus VR over there. So as the voltage increases, the capacitance decreases. And that kind of makes sense because you can imagine that this is your two plates and this is the distance between the plates. And as you're increasing the voltage, this distance is actually increasing. So that's what makes your capacitance go higher and lower. Um, But you have to remember this is a nonlinear cap, right? Why is it a nonlinear cap? Why I'm saying it's a nonlinear cap? Who can answer? Okay, come on guys, quickly. Is this a linear capacitor or a nonlinear capacitor?
And there is a square root of potential voltage in the equation, final equation.
Say that again.
There is a square root of potential voltage in the final equation. Cj is
Yeah,
equal to Cj0
yeah.
by
So is it linear or nonlinear?
non-linear. It is non-linear.
Oh, non-linear. Okay. So there is a voltage dependency. That is correct. But what is the real reason, circuit theory reason of being nonlinear? What fails? What theorem fails for a nonlinear element or a linear element?
Ohm's law.
Ohm's law, but there is no Ohm's law. This is a capacitor, right? So if I give you a circuit or anything, how do you figure out if it is a linear circuit or a linear system or not? What circuit theorem can you apply to make sure that you know that it
Ohm's
is?
law, sorry.
No. Ohm's law is for resistors. Yeah, so I think Abhinav got it right. So you apply superposition principle, right? So you apply superposition principle to see if it is linear or not. So you can apply superposition here. So it is always good to know. I think you guys know from people saying that, oh, it is voltage dependent. Yes, of course it is voltage dependent because the capacitor is varying with your control voltage. But more theoretical reason is because, if you apply superposition, the superposition doesn't apply to this. Whereas for the oxide cap, it does apply. So when we do circuit theory, we'll take these examples and show you how it applies or don't apply. So Ohm's law is just finding out the current voltage relationship in a resistive element, right? It doesn't tell you anything about a linear system, if a system is linear or not. The only way to find out if a system is linear or not is that by applying superposition principle. Okay, so I'm going to introduce something here, which we are going to use uh, in our VT calculation. And this is, this can be very, at times, confusing. So you just take it at the face value for now, and then there are a lot of literature references. You can go back and do it, right? So for example, so we just saw that when we take two semiconductor materials, so we take an N-type, we take a P-type, and when we attach them together, you get what's called a built-in potential, right? Um, in other language, you can call it as a contact potential also. So contact potential is mostly used if you're taking one as a semiconductor and another is like, for example, a metal, or one is a semiconductor, another is an oxide. And we'll see that when we are deriving our MOS equations. Now, the interesting thing about the contact potential is, so like, for example, here I've shown you have a material 1, material 2, you join them together and you're going to get a contact potential difference. And this is usually the same as your Fermi potential difference, okay? But the Fermi potentials are known only for semiconductors, but this is valid for any material. And that's why we're going to use, for this, we're going to use work function instead of semiconductor, Fermi level. So the work function is defined by the energy required, or the required to take electron from its conduction band to a vacuum level. Okay, so different materials have different work functions depending on how much energy you're spending from its Fermi level to the vacuum level. Okay, and essentially when you take these two materials and join them, the difference in this work function is the built-in potential, which is exactly the same as what you've done in PN junction. But the interesting thing about the contact potential is if I stack some N types of materials, then so let's say I have material 1, 2, 3, 4, 5, 6, some N type of material. And if I look at the contact potential, the difference here, contact potential, the contact potential is the difference of the work function only of the end two elements. So it is the work function difference between M1 and Mn. It doesn't matter what you have in between. Okay, they just keep canceling each other. They keep canceling each other. Ultimately, whatever is at the very end is all that matters. And so for example, let me take an example here. So let's say I take an example where I have a P plus a n plus, right? You find the contact potential, let's say it's 0.45 volts. Now you take a P plus oxide n plus, it's still 0.45. Now you take P plus, okay, metal n plus, still 0.45. Okay, so it doesn't matter what stack you put it in, ultimately the contact potential is just the difference between the work function of the very two end elements. Or let's say you have two metals at the very end, then they cancel and there is no contact potential. They just cancel each other internally. Okay, so just remember this. We'll use this during our VT potential. So sorry. Okay, so I'm just going to take, let's take a 15 minutes break. It's 3:15 now. Let's be back. Well, no, where's the time right now? It's 3:20 now. Let's take a 15 minutes break and let's be back by 3:15 and we'll start the next sort of topic. Okay. Actually, any questions before we go to the next one? Okay, so now we'll start looking at the MOS device. So we've been kind of building up to it now. So some of the passive devices results we have done, plus the PN junction stuff we have done, we'll use some of that as well. And this is kind of the core of essentially the CMOS course, is where you're kind of building the device, the primary device you're going to use. So just quickly give you the motivation. Like I said, from a digital design perspective, all your operations are done with 0, 1, which is, like I said, it's an abstraction, right? That 0, 1 may as well be 0, 5, right? Every time you say 1, you do 5. It doesn't matter. So it's just basically two states. You just have a two states, and based on those two states, you do it. But then how do you realize it? And, like I said, you have in circuits, the electrical parameters are voltage, current, charge, magnetic field, and so on. So we can use any of those, but the easiest and most popular one, which has evolved over time, is essentially using the battery voltage. So you have the battery voltage or your power supply of your circuit. You take that and kind of switch it to the output if you want to represent a 1, or you want to represent a 0, then you switch it to the ground, right? So essentially we're trying to build this device, and this device is basically, you can imagine it as a voltage controlled resistor, let's say. Ah, you can imagine this as a voltage controlled resistor. So you're essentially varying the value of the resistance across these two terminals by changing the voltage. This is your control voltage, and you're changing the resistance. So that's what we're going to look at in the next couple of lectures. How do we make these voltage control devices? So a lot of you are already used to BJTs, right? You have a control element which is base. The functioning is completely different in a MOS. And MOS, it's a capacitively controlled, so you don't have any DC current flowing through it. Now in finer technologies, you do because of quantum tunneling, but typically anything above 65, 45 nanometer, you don't see that. So what we are going to first do is derive the expressions, what's called threshold voltage. And the threshold voltage is basically, if I take this example, It's that voltage above which this resistor, you can say, turns on. Okay, so it's like you have a very high value resistance like mega ohms or giga ohms, after which value of this control voltage it turns out to be a lower ohm resistance, 1k, 100 ohms, 500 ohms, whatever it is, right? So and that's the key in controlling this device with the threshold voltage. So what we're going to do is we're going to look at uh, the sandwich, metal oxide semiconductor sandwich, and see what all decides this control voltage, this threshold voltage, at which this threshold voltage is a threshold at which the device becomes conductive or non-conductive. But before we look at the complete device, we'll just take the capacitive structure, the MOS, oxide, and semiconductor, and sort of derive the equation of how to turn on and off the channel, or turn on and off the resistor, basically. Okay. So, um, so we're going to start looking at this sandwich. Like I said, we're going to look at the sandwich, which is the metal oxide and let's say p-type. So in the languages we have been speaking a little bit so far, this is going to be your polysilicon. This is your silicon dioxide, obviously, and this is your wafer, right? P-type wafer. So now what we're going to do is we will apply a voltage across it. Okay, we'll call that VG as gate voltage. Um, so this is a voltage which is applied between the p-type substrate and the metal gate with oxide as the insulating air in between. Okay, and when you do this, because you have a voltage, there has got to be electric field, and this electric field obviously appears across the oxide. So you have some positive charges which flows from the battery and gets accumulated um, in the metal, or polysilicon to be more precise when we get to the devices. So let's consider metal here. So metal, and each positive devices will emanate electric field which will pass through the oxide because there is no charge in the oxide. This is the resultant electric field, by the way, because the example I showed you, you have some dipoles, but this is the resultant electric field which will flow, and it will, the p-type material has majority carrier is what? Holes, right? So it will drive away a hole. Once it drives away a hole, because it's electric field, right? If there is electric field and there is a mobile charge, there will be a force on it and it will move away. And when it moves away, it is going to and you can say, oh, why is it just not acting like a resistor where they're just continuously in a flow? But you can't have that here because you have oxide in between. There cannot be a continuous flow, right? So, but this electric field has to end somewhere. So that force allows us to knock out that positive charge, and that positive charge obviously gets absorbed in the battery here, which actually gets, you know, gets gets discharged here. So it's charge neutral, and so it builds this electric field, right? Now, if I start plotting the potential across it, you'll see the voltage. Um, Obviously, if this was a metal plate right here, this was a metal plate. If this was a metal plate, then you would have VG just end this at 0, right? Because the charge here is at the sheet. It's like on the very sheet over here. So it would end here. But because this is a p-type, and we have seen this in the previous equation, there is a depth to it, right? It just doesn't end abruptly. So which means that there is going to be a certain potential because the electric field continues, right? If it is a metal, the electric field will just abruptly end there because the sheet charge density is so high, it'll just end there. But because this is a semiconductor type, it'll seep in through it. And so that's why you see a potential at this surface, and that potential is equal to whatever is this electric field, the integration of that, right? Because you have a certain electric field here, you integrate that, you're going to get that potential here. And everything from here to here, it is zero. Zero, or whatever is this voltage here. With respect to this, it's 0. So if I plot it, you start with VG, you end with what's called the surface potential, phi S1. And then obviously, eventually, the potential just dies down inside the depletion and goes to 0. If I just plot the potential, you'll see that when there was no applied gate voltage, it was obviously 0. So the potential is this potential with respect to this ground. So it was 0. And then I apply a gate voltage. Uh, that gate voltage results in some surface potential here, which is this value here. And this is not drawn to scale. Actually, it should be somewhere here. So I apply a gate voltage and you get some surface potential here. Now let's increase it a little bit more. So we increase the voltage a little bit more charges come out, the depletion extends even further, which means that the electric field extends further, which means that this potential at this surface has to rise even further. So you can see this potential rises further. And I've shown this in this graph. The potential at that interface between the oxide and p-type now increases, okay? And we go further, increase it a little bit more. And then when you reach a point where this potential is equal to 2 times the Fermi potential of p-type material, okay? The Fermi potential, if you remember, that's the potential between the intrinsic and the doped Fermi potential. That's the Fermi potential. So once you reach 2 times of that, at the very edge, this will invert into a channel of n-type. So there will be actually n-type here, and there will be free electrons actually. Why it is 2πf? It'll be actually more clear when I show you the band diagram. So I'll show you the band diagram version of it too. But just remember that this surface potential with respect to this point here at the depletion point, if it is equal to or more than 2πf, then this channel will invert here and you'll actually have mobile charges. So I've shown this in green. So you'll just have mobile charges. Okay. So at this point, you tell that this channel has inverted and you actually have free carriers, negative carriers inside a p-type to be able to conduct it. Okay. And this is what's called the inversion. So you're inverting a p-type to an n-type in that just that thin region, not this whole thing, just in that very thin region. Okay. And the voltage at which this happens is called the threshold voltage. So I keep increasing the threshold voltage. And once this happens, the surface potential gets pinned to this 2πf value. After that, as you keep increasing VG, the 2πf doesn't change much because this now looks like a capacitor. You have metal on one side, you have like metal on one side, and this depletion is almost fixed now. Okay. And your voltage is now just rising above this, and this is pinned at fin, and your electric field is just increasing here. The charges are increasing here. Okay. And if I apply KVL across this loop, then I can show that VG is equal to the voltage which is dropped across the oxide plus the voltage which is dropped across the depletion, which is called the surface potential, which we have been calling the surface potential. And that's the gate voltage at which the channel turns on. And what's that value? That's what we're going to calculate, going forward. Okay. So, and this is the definition. So the definition is the threshold voltage VTN is the value of the voltage at which, when I apply that voltage VG across this oxide, when phi s is equal to 2 phi f. Okay. So let me repeat it. I think it was a little bit jumbled up. So the threshold voltage is defined as that voltage. Okay. And we call that voltage VTN. That voltage VG, which we call VTN, when the surface potential is equal to 2 phi f, which is the twice the Fermi potential of this p-type material. So that's the definition of the the threshold voltage. And that's the reason it's 2 phi f, because the channel gets inverted from a p-type to n-type. So now I have actually n-type material to conduct channel. Now you might ask like, oh, you already have a p-type, you have holes. Why don't you just use the holes? Yes, I can use the holes, but I have no way to control it. Every time I apply a voltage, it just conducts. Okay, so when I put the source and drain terminal, it'll be more clear. How does it become a control device, right? So in other words, VTN is that value where the oxide voltage, which is dropped across this for the surface potential when it is 2 phi f. And what is this oxide? What is this voltage across the oxide? It is this total charge, because it is at the point when this whole thing is inverting, right? So you can approximate, this is not exact because you have certain depth here, but usually the oxide depth is so much bigger than XP that you can approximate this to the total charge divided by the oxide, unit area oxide of this dielectric here, or in this case it's oxide. Okay, and what is this charge? This is what we have already calculated. You remember before lunch or maybe after lunch we did this huge derivation on a PN junction where we are calculating Q depth. So we have already have the expression. We'll plug that expression in, and that's your potential for which the channel will invert, and that's called your threshold voltage. But this is what is called the ideal threshold voltage. So this is a good start for us, but we'll keep modifying this expression. So you can see it's a function of whatever is your doping concentration of the P type, Fermi potential, obviously the permittivity of the material divided by the Cox, and the 2 times the Fermi potential. So in other words, you can control this value of the voltage by changing the doping, or you don't usually change it because this is the entire substrate. So I'll show in the next couple of slides how to change it, but it's a function of these parameters basically. Okay. Any questions so far? So this is the ideal definition for your threshold voltage. So we have 2 expressions, and there are a few more adjusting expressions which I'll keep adding, and we'll have a complete expression in a couple of minutes. But before I do that, any questions? Okay. All right, looks like see there's a chat question, but I can't see it. 1 second. It's very strange. I can't. Just give me a second. I'll just stop sharing once. Okay, now I can see. Okay, Sumant is asking, can you please tell me why did you take the modulus of the, because phi f for a, doesn't matter if it is N type or P type, the VTN is the modulus of it. So basically it is whatever it takes to reverse the phi f. So in case of a N type, the phi f is negative. In case of a P type, it is positive. But for both of them, the VTN is positive. That's why we take it. Actually, no, in this case, hold on a second. Make sure I understand which one are you asking. Yeah, in both the cases, it's positive. I mean, it comes from, okay, so the short answer is if I take it, then it'll come up with a wrong VG, because what we are looking for is the potential needed to invert the Fermi potential, right? So we are looking for 2 phi f for the phi s, and then if I have a p-type material, that obviously is positive, so you get the mod of it. If it is an n-type material, it's actually negative, but your VTN is yeah, in this case, it doesn't matter because it's obviously positive. But in your NMOS, when you do the derivation of NMOS, your VG, you're applying negative. Yeah. So yeah, that's a good question. Actually, in this particular equation, it doesn't matter. Actually, the sign and the modulus are the same. So sometimes I use the modulus in case if I don't want to confuse it. In a case of a n-type, which is the PMOS, I think you can either give the modulus sign and do a negative, because there you're applying negative voltage. So typically when I'm doing these derivations, I like to see which direction I'm changing the voltage, and I want to make sure the quantity is in that direction. So the Fermi potential is 0.45 volts. So I want to give 0.54 volts on on VG. Then I just take the mod of that to avoid confusion. But take a look in the derivations. I'm sure some of them probably don't use the mod, they just use the sign. But yeah, that's a good question. You don't have to in this particular, because phi f is positive. For this particular case, phi f is positive. Although yeah, in both cases it'll work fine. Okay, any other questions? Yeah, typically the signs, I sometimes, if I'm in doubt and I know the direction I have to go to, just take the modulus. You'll see when we do PMOS and NMOS, all the signs are negative. But when I started designing, I just wanted to avoid all the confusions, and I know which direction the voltage or the current needs to go, so I just take the mod of those values. So I'm not sure in the literature if this is in the modulus, but here obviously it is positive, so it should be the same. And I think for the PMOS derivation, you can take the negative of that, or the modulus, or just take 2 phi f, and that should work as well. All right, so this is, like I said, the VT and ideal. Okay, so what are the other correction terms needed to get to the final answer? And this is where the contact potential comes in. And I think I've already explained this, so that if you have two materials, then you get a contact potential between them. It's basically the potential at the contact point you get. You can measure it, because once you put a voltmeter, then the two ends become metal automatically, right? So essentially, if I try to measure this, then I'll put a voltmeter here, which is metal. So this will, so let's say this was, SiO2, and this was P plus, and I wanted to measure contact potential. So I put, a probe here and a probe here. But the moment I do that, then now this is metal, and they're the same Fermi potential, and then I will not measure anything, right? So that's the root of your reason for calling it contact potential. All right, so um, this contact potential is also what's called the flat band voltage. Again, the flat band voltage will be more clear when I explain it through the not explain it. I won't go deep into it. I think I like the charge model much better. It's much more intuitive rather than the band diagrams. Obviously, device physics guys, they like the band diagrams better, but it's okay. I mean, either ways you can prove it. So what? So now the term which I'm going to add is basically this contact potential, because uh, although I cannot measure it, but it is existing within this thing for me to overcome it first before I can do what I explained in the last slide. So in the last slide, I was explaining that I'm going to apply a voltage, blah, 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 and it'll invert a channel. But first I have to overcome this, right? First I have to overcome this contact potential. This could be a negative value. If it is a negative value, then you're basically undercoming this, not overcoming this. If it is a positive value, then you have to overcome this. And or the other way around, if you're looking at it from the built-in potential. Um, and so this is also called what's called the flat band voltage. So in our previous equation, and this is usually given by this expression here, which is essentially the it's like, and if you look at this equation, I think somebody was asking, is it the same as built-in potential? So you can see the expression is the same as built-in potential. So it's just how where you're applying this. So one place is called contact potential, one is build potential. Honestly, I don't know where one would make sense, other one wouldn't want. But the underlying principle is the same. So so now we need to add this to the VTN expression. So we had this expression before. So this was your voltage across your oxide, and this was your surface potential, which is required by definition. And then now we have to overcome this as well. So by the way, this I'm doing it because I'm assuming that it is in the opposite. So but the flat band voltage could be a negative voltage also, depending on what the sign is. So whatever it is, you just plug it in and you get a VTN value. And we'll calculate some of these values soon. Okay, so we take one example where the Cox is 3.45 femtofarad per micrometer square. So this is pretty much like a 0.18 or 0.13 micron technology. And you're given a doping concentration for the p-type, doping concentration for the metal, which is poly in this case, which is, you can see 10 to the power 19, which is pretty much degenerate. So typically you don't apply these equations there, but 10 to the power 19 is at the border. If it was 10 to the power 20, 22, then you couldn't apply these. And that's where you have to use the work function to explain it. Okay. And if you calculate the values, so you can calculate the flat band value. That's turned out to be, like, as you can see here, it's minus 0.865. 2phi is 0.579. And the Q depletion over Cox, you can see this is a pretty much a negligible term. So you don't, it's just pretty much not contributing to the VT expression here. So now if you add these together, you see the VTN is minus 0.25 volt. Okay. So what it means is that all the explanation I did so far, I assumed that the channel wasn't formed. You had to put a positive voltage to form the channel. But after calculation with these material, you saw that the channel is actually already formed, even at Vg equals to 0. You have to actually have to go negative to turn the channel off, right? So this channel is already formed. Okay, so before even if you apply a voltage, this channel is already formed. But obviously, and this is what's called a depletion mode device. But what we really want is actually an enhancement mode device, where we actually want, in case of an NMOS, we actually want to apply a positive voltage to turn it on. If the gate to substrate or the gate to source voltage is 0, then there should not be any channel on, right? So let's see how we can do that. So for the enhancement devices, what people do is, obviously you can't change the poly, you can't change the substrate. I mean, you can change the diffusion constant and all that, but your typical cases, if you try to change those, then it'll become very conductive. And then your rest of your devices will just become a really bad device. So instead, what people do is obviously they dope whatever it is needed for your resistivity, for your isolation and all that. Poly, same thing. And then once you do the calculation, like, in the previous calculation we did, we find out it's negative. They do a positive ion implantation here. So these are not mobile charges, they're fixed charges, but immobile charges. So you implant them. If you implant them, so now what you have to do is you have to overcome this as well before you invert the channel, because if there are these are negative charges. So if these are negative charges, negative immobile charges, then I have to put a certain amount of positive charges to cancel this charge first, right? Before I do any of that inversion and all that, right? So you have to add a positive VG here to do that. And this is what will make my VTN go from negative to positive, right? So we have example here where this is what I call the intrinsic VTN. So you have a flat band voltage, your depletion charge, which we saw is pretty negligible, and 2 times the Fermi potential. So given your doping concentrations for your poly and P plus, you're going to get a certain, and your thin oxide dielectric constant and the distance between the poly and the gate, you're going to get a certain intrinsic number, which I think we calculated as minus 0.25 or something like that. But I want a positive value. So what I do is I add a negative carrier of the value. So this is obviously should be mod, but you can understand is whatever is the electron or the ion charge times the ions per unit area, because it's kind of a sheet area. So you add that. So that's the total charge, right? So this is a total implanted charge, obviously divided by the Cox, because that charge divided by, it's a capacitor. So that charge divided by the Cox is the voltage I need to apply to overcome this, right? So that's the voltage. So this you can call it V di or something. So you have to add this voltage to cancel this charge first, and then you have the inversion you have to take care of, right? So let's take an example here. So if you take the previous example, remember it came out to be minus 0.25. Let's say we want to engineer this. So I'll do reverse, and we want to get a 0.678 volt threshold voltage, right? Which is typical, like a 0.18, 180 nanometer device will have 0.68 volts, which means that I need to make this term equal to 0.928. So this whole term should be about 0.928 volts. Okay. If I do that, then I'll get this number. To get that, I know Cox, I know the value of the charge of electrons. So if the value of the ions was equal to the charge of an electron or a positron, so I equate this. So I need 0.25. I know Cox, I know Q. I calculate Di, and that Di happens to be 2 to the power 10 to the power 12 ions per centimeter square. If I bombard this much ion implantation into this, then the VT will turn from minus 0.25 to 0.68. If you guys remember yesterday when I was showing you the process, CMOS processing flow, towards the end you saw where it says VT adjustment, right? So it takes actually your diffusion mask and does this ion implantation to do VT adjustment under the gate. So before you form the poly, you do this adjustment first and then form the poly, because if you form the poly first, then you won't have this this ion implantations, right? Okay, so this is the complete expression when, so I'll show you the body effect one later on, but this is the complete expression for your VT expression. So it depends on your flat band voltage, which is the work function difference between the two elements, your gate and the substrate, plus whatever depletion charge gets accumulated divided by Cox, which is a small number most of the time, then 2 times the potential, because that's what you require to invert the channel. And then depending on what you need to adjust the VT to, you do the implantation, ion implantation for that much. Okay. So let me stop here for a few seconds, a few minutes, and maybe take some questions. Any questions so far? No questions? Okay. All of you raise your hand who understood everything, or at least most of it, for this VT calculations. 2 hands. 4, 7. Okay, good. I hope you can solve the problems. Okay, looks like fair amount of people, and looks like there are a fair amount of people who just they don't raise their hand when I say if you didn't understand. They don't raise their hand when I say did you understand? So I don't know who's watching those videos. Um, all right, so no questions. All right, so looks like there is one question from our usual suspects. Why is it called flat band? Good question. Like as I said, I'll explain this VT thing two different ways again. One is showing you again the charge method, and one showing you the band gap. I'll just, this is what I showed you a little bit detail. The next two ways I'll kind of quickly go through it. But when I explain the band diagram one, it's just a term. So just remember it's a term. Basically, the key thing is that, see, you guys get, you guys get so attached to these terms. Is it positive resist? Is it positive? What is it? Just understand what it is doing, right? You have a contact potential and you have to overcome that. So just remember that. But no, it's a good question. I'm not trying to discourage you. It's a good question. There is a reason why it's called flat band. So I'll explain it when I show the band diagram. So you probably would have guessed it. So you saw the band, when you take two material and connect them, you saw the bands bend, right? Because you have two materials of two different Fermi potential. But thermodynamics says that the Fermi energy level should be same for a material which is in steady state. With steady state in the sense there's no electric field or magnetic field imposed on that. But if that's the case, then the conduction and the valence band has to bend. So this potential is to actually flatten that band and actually bend the Fermi potential. Okay, so take it from steady state to a non-steady state. Okay, any other questions? Okay, so first in the fabrication process, before applying SiO2, we do ion implantation to adjust the VT. Yes. Actually, the SiO2 itself depends on which SiO2 you're asking. If you're asking about field oxide, by the way, this is what, you know, just when you just say SiO2, it's not complete in the sense that, you know, the SiO2 is also used for as a mask, right? So, but it is also the insulating air before you start doing the metallization. So if you're asking about, do we do it before we do the metallization? Yes. But the SiO2 is also used as a mask for doing the ion implantation. So they'll do a thin SiO2, put, what do you call it? Photoresist on it, mask it, take the SiO2 off, then do the ion diffusion, because the diffusion will diffuse into the silicon, but not into silicon dioxide. It'll contaminate a little bit, but then you actually dissolve all the SiO2 off and then do the processing again. So yeah, so you use the mask to do the VT adjustment, but you want to make sure the VT adjustment is done only on the channel area, not the other areas. You can do it on the source and drain areas because you're doing ion implantation on the same type as, well, is it the same type, P plus? No, you have to, yeah, that's, I'm not sure if they use the diffusion mask or the poly mask. I think it's the diffusion mask. So it goes into the source and drain as well. But, you know, they do the source and drain implant after that. So I guess the implantation for VT adjust is so small that doesn't matter if it is in the opposite direction. Yeah, I'm not 100% sure about it. Okay, any other question? Okay, there's another question. It will not work in case of negative threshold voltage in enhancement mode. Not sure if I understand the question. It will not work in case of negative threshold voltage in enhancement mode. Not sure if I understand the question. Enhancement mode device. The enhancement mode NMOS is a device which needs positive VT. Enhancement mode PMOS is a device which has a VT negative VT value. Okay, so I'm not sure what you mean by it will not work in case of negative threshold enhancement mode.
Maybe he's asking for an NMOS.
This is NMOS.
Yeah.
Yeah, this is NMOS, by the way. Maybe was I saying PMOS? Sorry if I was saying PMOS. Yeah. This is NMOS. Okay. So it's not PMOS. Maybe by mistake I was kept saying PMOS, PMOS, PMOS. Yeah, this is NMOS. So for NMOS, this is yeah, it's a P-type substrate, but it is NMOS. Maybe by mistake I was saying PMOS. All right. So looks like, yeah, you got it. All right. So like as I said, I will explain this. Oh, there was another term I forgot to mention. And this term is actually the impurity inside the oxide. So what happens is when you do the oxide growth, because you are doing all this diffusion and this and that and the metallization, there is always impurity which diffuses into the oxide. So for example, if you're doing silicon nitride and you have some ion implantation, I mean silicon dioxide, and you have ion implantation, some of that ion will actually diffuse into the silicon. So this process, there is always a little bit of impurity inside the silicon, and whatever that charge is, if it is a positive charge, for example, I need to put a negative value to so your V, it will add a negative voltage value to the VT expression. If it is a negative charge, then it will add a positive amount to your VT expression. But you also need to overcome this as well. But these are your smaller terms, and these are sort of the parasitic terms for you. Okay. So before I show you the other ones, just quickly the MOS capacitance. So we in IC design, you're always like just doing MOS capacitance for everything, right? It's dragging to you as a load or using it as a capacitor, but it's actually a very linear capacitor after the channel turns on. So you can see from this sort of this graph, as the voltage is increasing, the channel doesn't form. Obviously, we have been saying that the channel doesn't form till it is VT0, but in reality, the channel turns on, kind of before that. So you almost have a BJT kind of operation. So this is what's called a subthreshold operation, this region. And actually, a lot of the low power analog devices we operate in this region here. And once the channel is completely formed, it looks like a capacitor of the value Cox, right? Because it's like two plates over here, oxide. So your um, uh, capacitance per unit area is whatever is the capacitance per unit area for your silicon dioxide. And your total capacitance is the gate area times Cox. And if you want to calculate the charge, then obviously the gate voltage, the excess gate voltage. So we call this excess bias, excess voltage, V on, a lot of names for this voltage. So whatever is the excess bias above the VT times Cox times W over L, that's the charge which is going to form here. So this is kind of a nonlinear capacitor in the sense that the capacitor doesn't turn on till VT, but once the capacitor turns on, then it is a linear cap. So um, it's kind of linear and nonlinear at the same time. Okay, and I show that the sheet charge, which is the charge per unit area on the gate, is equal to Cox times Vg minus Vt0. Basically, this equation divided by the area of the gate. Okay, so now I'm going to quickly show you the same thing, and but show you in a sort of a charge fashion. So what I showed you is more of a showing you the potentials across it and how the potentials are varying based on those potentials and electric field. What is the value of VT? And now I'm going to show you from a sort of a charge perspective. It's almost similar to already what we have explained. So we've already seen that what happens is when you take a P-type semiconductor with certain doping concentration, and you take the metal, which is in our case polysilicon, and you take a sandwich, the channel actually gets formed already because of the whole work function differences. Okay, and again, this will be actually more clear if you do band diagrams. So some of the things are actually easier to explain in band diagrams than they are doing this. But we did calculate and see that the charges will get formed, right? So now what you do is you apply a voltage which is equal to this phi ms to remove that charge. So now this is what's called a flat band, so that you don't have any charge accumulations anywhere. Not necessarily, but that's usually what it is. And then you apply the potential such that this surface potential is 2πf with respect to depletion, and the oxide potential difference for you to apply that QB charge, which we have already discussed in length. So this is QB over Cox phi. Once you do that, then you form a channel. Then you have the depletion first, and then you form a channel, right? And but on top of that, like as I said, there are usually some traps charged inside the thing, and mostly actually on the surface, because this is where you stop this is where you grow the silicon dioxide. So if there is some impurities before here, they get trapped on the surface. And this is in analog design, this is a huge problem, because they actually create what's called flicker noise. So low frequency flicker noise is what is created. So if you have had ever some bad amplifier or bad phones, and you hear this hissing sound like shh, like a kind of hissing sound, it's mostly because of these trap charges, which is okay. And so that's the voltage which is required to invert the channel. So you first come over the flat band voltage, not first, but in series basically, and then you give the voltage to come over this impurity charge. So for example, if this was positive charge, then this would be reverse. And then the voltage which is required to bring this potential to 2πf, and plus the voltage which is required to create an electric field such that you create a depletion region here to create this phi. So it's convoluted, and that's your VT. So that's your expression for your VT, the threshold voltage. I just showed this to show you, what is the, like as I said before, when we have semiconductors, usually we take the Fermi potential differences. But let's say you have from a metal to a semiconductor, there is no, so there is a Fermi potential, but that's your conduction band basically. So that's why we use the work function, because the work function is basically it's like the you kind of, instead of going in this direction, finding out what the potential difference, you're going to infinity back to the work potential of this guy, and then back to the Fermi level. That also gives you uh, the work function difference. So okay, now I'm going to quickly show you the same sequence but with the band diagram. So what happens is, when you join this metal oxide, you take this sandwich, and if you take the band diagram of it, you can see because the Fermi level needs to be same for this entire conglomerate, to do that, because the bands are different, the work functions are different, the bands will bend in a certain direction depending on the type of material. So here you can see, if it is a p-type and it's a metal and an oxide, the band actually bends in the direction of where the channel will get inverted. In fact, it does get inverted. Now you apply a voltage such that these bands get flattened. Now you can see there is a difference between the Fermi potential. That's your whatever band potential. So the Fermi potential by definition for a steady state needs to be same, but now because it's not steady state anymore, because we have applied electric field across it, then that difference, whatever the difference was here in the bend, that voltage difference we apply across to flatten this band basically. Okay, and that's why it's called flat band voltage. Once you do this, then you start bending it again, applying it, and you bend it so that it goes. So now you can understand why it's 2πf if you look at this diagram, because this is a p-type material, right? In order to make it an n-type material, so if I take so let me take like the cross section of, so so obviously if I take this cross section, it just looks like a p-type material, right? If I take this cross section over here, right, And if I draw the band diagram, if I kind of exaggerate it, so this is EC and this is EI and this is EFP, which now is actually N, right? And this is your valence band. So if I show you, so if I took a slice of this and did the band diagram like this and showed it to you, so oh, this is N type, right? And it's an N type of the same magnitude as the P type, because this, whatever is this phi N, is the same as whatever you had phi F over here. So that's why if you have a certain type of p-type material, you want to invert the potential, Fermi potential, by the same amount, which means that the total potential you want to apply across is 2 phi f, right? So that's the reason why we keep saying it's 2 phi f, 2 phi f. So once you do that, the channel inverts, you have a electron attracted to the surface. Now what you can do is, now this is where, so till now it's a capacitor. Now you can put a N plus material here, put N plus material here, and apply some voltage here and do conduction in between. And then if this voltage is less than VT, then because the majority carrier is electron, there are no electrons here, then there will be no conduction. Okay, just minority carrier, which is very small. And that's the whole goal of this exercise, is basically to make this device voltage control. So having like a voltage controlled resistor, basically. Okay. All right. Any questions so far? Hopefully some of the questions you asked has been answered. Some of the questions you just have to read yourself, because like as I said, um, I don't do device physics on a daily basis. So for me, it's difficult to explain some of the concepts intuitively. So you just have to read some good books and understand it for yourself. No more questions? Okay. So like as I said, now that you have a channel, you can apply N plus N plus region here, and that's how you create your NMOS device, right? So you attach two semiconductor areas with a lot of electrons in them, majority carriers. And because if you have that and you have formed a channel after you make your VGS equal to VT0, then you can conduct current through this, okay? But when you have a device, you don't always connect this source to the same voltage as the bulk, okay? Here I'm showing that the source and bulk is shorted, as well as the drain. Obviously at the drain we apply some voltage for the current to flow it. So not always this is connected. For example, I'll show you even when when you do combinational gates, you'll see that your NAND gate, for example, will look something like this. So this is A, this is B, this is your VDD, this is your output, and your NMOS is two series devices. And A, B. So this is a NAND gate, right? Now, if you look at this device here, this is the bulk, which is all the bulks are sorted to ground, right? Because the substrate here is, you can't, here you don't have option. In twin tub you have option, but here you don't have option. So mostly we try to keep the bulk at the same potential. But when this series transistor is on, this voltage is not at ground. It is whatever the current is flowing through it and whatever is the channel resistance, this voltage is sitting at that. So which means that this source voltage will be sitting at some higher voltage, right? It won't be sitting at ground here. Now, when that happens, your effective VT actually changes. So you can see if I apply some source bulk voltage to this depletion area, because now what you're doing is you can see this is a reverse bias diode, right? So this source, yeah, this is a reverse bias diode, right? So, and this is your contact area, and when you're applying this potential, this depletion area now will increase by this whole green shaded area which you have shown, right? So now the question is, what does the VT value change by? Because now what you have done is, um, we did this calculation where we said, okay, maybe if I show you the equation, that'll be more. So we have this extra charge now. So I'm calling this QB0. So QB0 is the total depletion charge when VSB was equal to 0, right? So QB when VSB is equal to 0. Now I added some, I lifted the voltage from ground to some value, and then this depletion area increased, right? Because you remember we did the junction diode where you apply the reverse bias voltage, this junction area will decrease, which means that you have this extra charge now. So that extra charge will result in what I need to do on the gate to keep the channel the channel potential back to 2VF, right? So if you remember, we did, if I write this equation again, so you remember, okay, let me read, it looks like I didn't write, let me rewrite the equation here. So remember, we wrote the equation as VT and for VSB equal to 0, so VSB equal to 0, it was the flat band voltage, right, plus QB by Cox plus 2VF plus Q impurity over Cox plus what is the other term I'm missing, and the adjustment QDI over Cox, all this, right? But the key one is here, right? So we applied a certain voltage to not overcome, but the voltage required to get this QB such that the surface potential is this surface potential phi s is equal to 2 phi f. And now what we have done is we have kind of now it's counterintuitive. It might look like, oh, what you have increased um, uh, the depletion charge, but this depletion charge is increased not to increase the surface potential, but just as a diode. But that also has an effect on the surface potential, which means that I need to increase this VG by this amount again, by the difference of QB minus QB0 over Cox to get it back this surface potential to 2 phi f. Okay. I know it's not very, like intuitive, because like as I said, if you're looking at QB and you're saying, oh, it actually increased in the same direction as what you're trying to do, but we were applying the voltage from gate to substrate. Now you're applying the voltage from source to bulk. So that charge needs to be again overcome by gate to source such that Q phi s is equal to 2 phi f. And that voltage is whatever is the difference in charge divided by Cox, you try to negate it back again, almost bringing it back to the original structure. Okay. Or in other words, what you're saying is that make it look like that this extra charge came because of your application of yeah, maybe that's a good way to explain it. So this charge which you got, make it look like as if you got it because you applied a gate voltage. Now obviously once you apply a gate voltage, this depletion is going to change a little bit further, but that's fine. We are going step by step. We are saying what is the voltage we need now to make it look like as if this extra charge was created by the gate voltage rather than the source voltage, because that's what will bring this potential to phi s. This potential will not bring this to phi s. The gate potential will bring this to phi s. Is it sort of clear? So basically, the bottom line is, if your source voltage is higher than your substrate voltage, your VT increases by this amount over here. And again, we have done these calculations in pretty much detail, and you can express this as this term, which is basically your process term, then 2 phi f plus the source to bulk voltage minus 2 phi. And you can see once I make this to 0, then it turns out to be VT0. VT0 is basically this term here, which is the threshold value, threshold voltage at substrate to bulk, source to bulk value 0. Okay, Max, is this clear, or you have any questions on the body effect? Any questions on the body effect? So the bottom line is, if your source and bulks are not shorted, if it is a different value, and in case of a CMOS, in case of a NMOS, it's a higher value. In case of a PMOS, it's a lower value. Otherwise, this diode will get forward biased. The source to bulk bar diode will get forward biased. Okay. If it is a different value, then your VT will increase. And that's why, for example, in analog design, we try to keep the source bulk tied together as much as we can to avoid high VT. And so you lose headroom. But the downside of tying something like this, let's say, for example, in this case, for example, you say, no, I can't afford to have a different VT. So I'll just draw the series device here. So you say, no, I can't afford to have this. So what you do is you tie this. Now in a locus process, in this process, you can't do this because that'll short your ground to this voltage. But in twin tub, you can do this, or deep N-well process, you can do this. So if you do that, so now all the source bulk are shorted for those region. But the problem is, this is a big diode here, because that's a diode between the source and bulk and the substrate, and this adds capacitance. We derived the equation just a while before, so this will add that nonlinear capacitor Cj, and this will slow down your devices basically. And that's the main reason why you can't just keep. And also layout area. So your layout area will start becoming larger and larger, because now you have to separate them in different wells, and the well separations design rules are longer and larger and so on. So when you do layout, it'll be more clear. Okay, any questions on the body effect? Yeah, I'm just writing this equation. Basically writing this term as a gamma. That's how you'll see in textbooks. Okay, so you don't have any questions. That's all I have for this thing. So tomorrow what we'll do is, now we'll do the IV characteristics. Now we want to see what is the relation between the gate voltage and the drain. So gate to source voltage, drain to source current, then drain to source voltage, drain to source current. So we'll see all that relationship, plus all the parasitic capacitance, which is in a MOS device you have, and the origin of that. We'll look at that. Okay, any questions from what we've started? So basically what we did today was, we looked at capacitance. We started from the very basic and looked at what are the parameters which control capacitance, how to calculate capacitance, and then kind of showed you why routing capacitance for finer technologies are getting worse because of the sidewall caps. So we looked at sidewall caps, the fringing caps, and the bottom plate caps, And we check that with some of the design documents, and they are in the same ballpark as what we calculated. And then we also looked at resistors, right? So what is the resistance of a metal? How do you calculate it? Contact resistances, how do you calculate it? And what are parasitic resistances and capacitances, and what happens after you extract them, and so on and so forth. And then we started the semiconductor, just introduce you to semiconductor band diagrams, showing you PN junctions, and we derived a bunch of equations for the reverse bias diode, which we used for our MOS equations. And then obviously after the diodes, we started with a MOS, where we just derived MOS as a not three terminal, but a capacitor, two terminal capacitor, and how the definition of threshold voltage, and we derived a expression for the threshold voltage as well. Okay, and so tomorrow I'll do some questions and put it, but we'll put some reading assignments also on the GitHub page, maybe by tonight or tomorrow, and you can start reading some more, solve some problems, and like I just keep saying, that's the only way to digest this material. Otherwise, the half time for this material will be like a day. You're going to forget after a day, or even an hour. All right, Santanu, do you want to add anything, or?